How can we find W perp if only W is given? Well, often our subspaces are given as a span, say W1 until Wk. Now you can prove that any vector orthogonal to W1 to Wk is also orthogonal to any vector in the span of W1 to Wk. Maybe you've already done that, otherwise try this yourself. The converse is also true. Any vector orthogonal to all vectors in the span of W1 to Wk is also orthogonal to W1 to Wk. This one is much easier to prove, almost trivial. This means that if you want to see whether a vector is orthogonal to W, it is whether a vector is in W perp, we only need to check whether a vector is orthogonal to W1 until Wk. And that is how we are going to find W perp. So suppose I've given some W as a span of k vectors, and I want to find a V in W perp. So what I need to do is to check whether V is orthogonal to W1 to W2 until Wk. So I have to check whether the inner products are all 0. So I will get here k equations which are all 0. So let's see how that works in an explicit example. We take a span of two vectors in R3, so this will be a plane. And I want to find a V, say x, y, z, I don't know x, y, and z, in W perp. So what does this mean? V has to be orthogonal to 1, 1, 0 and orthogonal to 1, 1, 1. So we find V in 1, 1, 0 equals 0 and V in 1, 1, 1 equals 0. So that gives me two linear equations. This one yields x plus y plus 0 times z, so x plus y equals 0. And the second one, we have x, y, z in 1, 1, 1, so x plus y plus z equals 0 as well. So any vector V and W perp has to satisfy these two linear equations. Well, this gives us a linear system, and we know how to solve a linear system. We make the augmented matrix, we use row reduction, which is in this case very easy, it's only one step, and we solve the system. We see that the z equals 0, second variable y is 3 and x equals minus y. So we write the parametric vector form, v equals y times 1 minus 1, 0. Then we have our solution of the system. And then we see any vector in W perp is of the form multiple of 1 minus 1, 0. That means that W perp itself is the set of all linear combinations of 1 minus 1, 0 or all multiples of 1 minus 1, 0. That means that W perp is the span of 1 minus 1, 0. So there we have found our W perp in an explicit example. We have some kind of shortcut in order to do this, because what do we see? Well, if you have two vectors, what did we do? We put them as rows in a matrix, set 0 on the right hand side, and solved a resulting linear system. So we're basically looking at some null space. So how can we do this? If we have n columns, say in the matrix A, and W is the span of those n columns, that means W is the column space of A. That means A1 in V has to be 0 up to An in V has to be 0. You can also rewrite this in terms of a matrix equation. If you put all those equations in a matrix, that means I have to put A1 as a row, V as a column equals 0 gives the first equation, A2 as a row times V equals 0 gives the second equation, and so on up till n. Then I get a matrix equation A times V equals 0. So the V is in W perp if it satisfies this matrix equation, or in other words, if V is in the null space of A transpose, because you have to put them as rows. So that's kind of a shortcut way to determine W perp. So in summary, the perpendicular of col A equals, as we saw, just the null space of A transpose. And if you interchange rows and columns in col A, you get the row space of A. If I interchange rows and columns on the left-hand side, I also have to do it on the right-hand side. But if I interchange rows and columns on the right-hand side, the null space of A transpose just becomes the null space of A. So, there we have two shortcuts in order to compute a W perp. However, more important than just memorizing those shortcuts is to remember how the procedure works, what you are in fact doing. It's not so hard at all to memorize those steps. So, I would advise you memorize the steps and be able to derive such a result yourself.